Hey everybody, so today I'm going to be going over all the CTF challenges from the NahamCon CTF. I've actually already done this once. I had it timed perfectly to finish and have it uploaded like right as the CTF ended, but yeah, somehow I screwed up the video and it was all basically useless. So if I sound bitter and jaded all video, that's why. Anyway, so I'm going to have this divided up chapters, so if you want to jump to a specific problem, you can, and then I'll try and remember at the start of each problem to do a little cliff notes. So basically, if you just like wanted to satisfy your curiosity on what you should have done, you don't have to like listen to me babble for a while to like figure out what it is you should have done. Then I'll do the challenge, kind of go over each challenge. I'm not going to go like super in depth. Crypto's kind of hard because there's a lot of math sometimes, and it's like how much math is too much math. But I figure if you're watching this video, it's probably because you tried one of these challenges and were frustrated that you didn't get it or just didn't quite understand it, how it worked. So I'm going to try and kind of like go over it and hopefully hit the right level of it makes sense, but without bogging it down like too much in math or details. So yeah, with that said, I guess let's just go ahead and jump in. So the first one I'm going to do is Unimod. So cliff notes on this are not very, well, they are very cliffy because basically it's just do this in reverse. So basically what's going on with this is if you go over the code, this right here, this hex number is a really big number. It's like 65,533, so almost to the 16th. And the ordinal values for characters, all the ASCII characters, which is what we're going to assume the flag is, especially since we know how it starts, is going to be less than 128. So the fact that we're going to modulo this, which basically means kind of like take the loop over, take the remainder, however you want to view it, means the odds are randomly that we got close enough to go over the top are pretty remote. So effectively, we can just kind of ignore this. Probably the confusing part of the challenge is just the fact that you're like, oh, what do I do with this? But if you see here, these are, I'm assuming from the challenge name, just Unicode characters. But so like they have an ordinal value just like any of the other ones. So that one is 39,239, which we can actually use that to tell that our randomly chosen K wasn't near enough to loop over, because if it had, it would have been something really tiny. So basically we can just, like, we know how the flag starts, like it starts with an F. So we can find K by just subtracting that value from F, right? That was the first character. We know the first character matched up with the F from the flag, so we pretty much know that that is probably the K value. Oops. So yeah, basically we're just going to reverse this. So we'll take the ordinal values of each of these in a row, subtract K from it, and turn it back into a character, and that's how we will solve this challenge. So let's go ahead and do that real quick. So we will we'll read in that file. Ciphertext, we'll read it, we'll strip off a new line if there are a /n line break thing if there's one at the end. Then basically, like, we already know the K, but we can get it programmatically, same way we did manually in the interpreter. So we'll take the ordinal value of that first symbol and we'll subtract the ordinal value of F, since we know that's how the flag starts. And then we don't know anything about our flag now, and then we will loop over every one of those characters, and then we will just add it to the flag, we will get the ordinal value of the character, subtract K, and turn that back into a character, and that should be the flag. So that's basically exactly the reverse of what we did here. So we added, now we're going to subtract. So we're just reversing it. And then we will print out the flag. And unless I typoed, we should be good. And I typoed. Stip. I'm gonna go ahead and lie and say I didn't make a single typo in the ruined footage, so you can't prove me wrong. So there you go. That's our flag. That's the first challenge. So that one was pretty straightforward. Let's go ahead and jump to the next one. I'm gonna go ahead now and we'll do this XORROX. So if you download, what do I have? The output and the code itself. So if we look at the output, we've got, I'm going to go and break it just so it looks a little easier. We've got these two lists here. And if we look at the code, we see we're reading in a flag, and then we're generating a bunch of random integers between 1 and 256, which is the same, a byte is between 0 and, all byte values are 0 to 255. So basically we're getting a bunch of random bytes, as many bytes as the flag is long. So you can kind of assume what we're going to do is XOR the key and the flag, which you'll see is actually happening right here, right? The index of the flag is getting XORed with a V, which is coming from this key. Now this other XOR thing, this list might be a little confusing. But what we're going to do is, if you kind of like step over this function, or not function, it's a step over this, this loop here, you can see what it's doing. It's going to enumerate the key. So we've got some list of random bytes, and we're enumerating it, which means it's going to get the index and the value for each one of those, and then go through the list. And then here we've got this K. And then what's happening here is now we're starting at whatever the index is, and we're counting down to 0. And then we're going to XOR K with each position in the key less than J. So that might kind of sound confusing. So let me go ahead and go over it with my little tablet thing. And hopefully this all shows up, because this is part of what screwed everything up last time. But so basically, for the sake of brevity and making sense, I'm going to actually change the name of this XOR, this array here. I'm going to call T, because it'll be easier to write. So we've got this T array, and we've got our indexes and blah blah, and then we've got a key, which is an index of a bunch of random bytes. So we've got our blah 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 blah, however long that is, and then in this function here we've got this K. And basically, if you step through, what's happening is the result of K is getting appended into the array T, because I remember I renamed XORROX to T. So in effect, what's happening is like T. Well, and the other thing is, so let's go through it. So the first time index is 0, the first value of the key, we get K equals 1. For J in range 0, 0, -1, it doesn't do this because the numbers match, right? This last one is never included, so it skips that, and it appends to the XORROX, which we're calling T. It appends K, and if we look, we see that's 1. The next time through, we're going to index value 1 for whatever that key is in the key list. We start out at 1. We're going to go through for the first time, so we're going to XOR K with the key in position 1. and then we'll append that to the array. So then the next time through, it's going to be index value 2, whatever it is. So it's going to be k is equal to 1 XORed with the key at position 2, XORed with the key at position 1, and then it's adding. So if you see that, so we know that T1 here is actually going to be equal to 1 XORed with K1, whatever the value was in this position of the array, and that was T1. And then we know that T2 is going to be equal to 1 XORed with K2 XORed with K1, right? And we just keep doing that. T3 is equal to 1 XOR K3 XOR K2 XOR K1, and then so on and so forth. Now, a few properties of XOR that you need to know if you're not familiar. Anything X, a little more room. Actually, that would have been good. Anything XORed with 0 is equal to itself. So XORing with 0 does nothing. Anything XORed with itself equals 0. Another useful one is, so XOR is associative. So if you have A XOR B XOR C, and that equals, we'll say D, it doesn't matter if you put the parentheses there or if you do A XOR B XOR C, right? It doesn't matter how you do it, it ends up the same. And the other property is it's communicative. So it doesn't matter if you do B XOR A XOR C, that's the same thing as C XOR A XOR B. Like, it doesn't matter how you do them or in what order you do them, it's always the same. So those properties mean that we can very easily reconstruct the key, because basically all this is kind of a recursive. Let me go ahead and do T4 as well. So 1 XOR K1 XOR K2 XOR K3 XOR K4. Like, if you look, this is basically a recursive, kind of recursive setup, right? So T1 was K1 XORed with 1. Well, look what's happening in T2, right? We could actually rewrite T2 as K2 XORed with T1, because with these properties here, like I said, it doesn't matter how you write them. So K1 XORed with 1 we know is the same thing as T1. So T2 is really just K2 XORed with T2. And then you can do this, you can see the same thing with T3, right? We've got K3, K2, K1, 1. Well, that's exactly what T2 is, except there's an extra 3 in it. So like T2 or T3 equals K3, the third value in this K list, XORed with T3. So in effect, we know that Ti is equal to Ki XORed with Ti minus 1. Well, like, let's write it out by hand. Let's XOR T3 and T2 together. So if we take T3, which is K3 XORed with K2 XORed with K1 XORed with 1 XORed with K2 XORed with K1 XORed with 1. Well, like we showed earlier, it doesn't matter what order you do these in, so we could rearrange all these so that it's basically K3 XORed with K2 XORed with K2 XORed with K1 XORed with K1 XORed with 1 XORed with 1. And we showed one of the other things is anything XORed with itself is 0, so these all just go away and you're left with K3. So we have a very easy way to get the key value. So it's just, we use that right there. We just rearrange it as Ki equals Ti XORed with Ti minus 1. So we can now just go ahead and jump in and write our solution. Now we can't get this, recover this first value because there is no, or we can't recover what the first value of the key is because there is no I minus 1, right? There's no earlier one. But we can recover the entire key just from using that. So we'll write XORROX solution. And then we'll rename that T, just so it follows all the jibber jabber I just went over. And then we can simply say that we use some list comprehension here, and we'll say that key, what did we say it was? T I XORed with T I minus 1 for I in range, and we'll start at 1 because, like I said, we can't recover the 0th one, but we don't care because we know the flag starts with F anyway, to the length of how long T is. And then we saw that, like I said earlier, the flag is XORed with the key. So what we have is we have that the encoded was equal to the flag XORed with the key. Well, again, for the same rules, we can now just XOR the encoded, which we have, with the key, which we're about to recover, and that will equal, and that will equal our flag. So now we will just go ahead and do that. So, we're going to go ahead and we're going to say our flag is equal to, well, we know it starts out with F, right? And that's the one we're not going to be able to add to it. So we're going to add the result of XORing the key with and the encoded. So we'll do another list comprehension. Let's build it up. We're going to say A XORed B for A, B, and we're going to zip the key array, which we created with the encore array. But remember, we don't want the first one, or encore, encode array. We don't want the first one, so we will just zip together key and encoded, but we'll start it at 1. And so this is going to match those all up, XOR them together, and that's going to give us numbers like byte values. But we don't want the byte values. We actually want it to be characters. Well, this is going to give us a list of characters, but we want it as a string all joined together, so we can just do like that. And now we can print that out, and we can run that. Bam. So there we go. Okay, so let's go on and let's do the baby RSA one next. So actually, I'll cut these into sections for the timestamps and the clips as well, because there's three questions. So it's kind of like 3 different little parts. So let's get to quiz. So cliff notes on part 1. Basically, if the way RSA works, if you can ever factor in and get the primes it's made of P and Q, then you can break the encryption. So if this number is small, we can factor it, we get P and Q, and that's how you do it. So to go over it a little bit, if you're completely unfamiliar with RSA, you have a public key in and E, where in is a modulus. It's a number made up of, it's the product of 2 prime numbers, P and Q. and then you have a private key, which is in and D. Now D is the inverse of E mod phi. So basically E times D is equivalent to 1 mod phi of n. Now I won't go into the math here, but basically this is kind of like where all the magic happens. And what this allows us to do is, so normally you take a plain text, you take a plain text, you convert it to an integer, like we don't worry about how or what or how, but you take that number then and you raise it to the power of E mod n, and that is how we get our ciphertext. And then to get the plain text back, you can take the ciphertext to the D mod n, and that's how you get the plain text. Now, again, the math for why this actually works, how to get D, and why this stuff here actually works is actually pretty cool, but I won't go into that. But what I will say is that phi, what you do need to know is that phi of n equals p minus 1 times q minus 1. And this is basically what allows, it's kind of like part of the security of RSA, right? Because to get phi of n, you need to know what P and Q are, right? It's really easy to calculate phi of n if you know P and Q. And if you know phi of n, then this formula here is also really easy to solve. So kind of the trapdoor function in the RSA is that it was easy for us, it's easy for us to find D, the person who created it, because we made n, we picked P and Q, right? We know what P and Q are, we picked them to make n. Everyone else who doesn't know that, they can't figure this out. This is too hard to figure out without P and Q. It's too hard to find phi of n. So they can't use what phi of n is in order to get D, because they need to know phi of n to get D. But we know phi of n because we picked it, or we picked P and Q, so we can find D. So that's kind of the security. That's like a trapdoor function. It's easy one way if you know it. It's virtually impossible the other way. So that's kind of how that's going to work. So for this function, for this problem, this number here is way too small, and that allows us to we can go to factor db, and we can factor that number. We can factor that number, and so we see that the factors of that number is, here is P and Q, basically. So when you have P and Q, it becomes, like I said, if you know P and Q, you can break RSA very easily. So let's just copy this stuff over. Oops. So now that we have P and Q, we can find out what phi was. Like I said, phi was equal to P minus 1 times Q minus 1. And then D is equal to the inverse of E mod phi. And then the plain text is equal to the ciphertext to the power of D mod n. So that is our answer. So as you can see, if you can factor in and get P and Q, then it's just super simple to then recover the plain text. So now we're going to go on to number 2, and it's taking a second because it's a big number. So Cliffs for part 2. So this time the number's way too big, we can't factor it. But there's another problem in that the E is too small for what their plain text was. So basically, we are just going to take the cubed root of this number, and that will be our plain text. So there's your cliffs. Oops. I'm just going to copy these. So to try and kind of maybe explain that a little better, so it makes a little sense why this is the case. Like if we look at, like, let's say for example, if we were going to send the private, our secret message is 123, and let's say we made our encryption exponent, we picked a really, really bad one, we made it 1, right? Well, that's obviously dumb, because anything to the power of 1 is just itself. So now our plain text and our ciphertext is the same, it's the same thing. Well, conversely, not conversely, but similarly, in this instance, picking 3 would be pretty bad, because our modulus is so huge that when we raise our tiny message to the power of 3, like, we just get this small number. Now, kind of the way it works is it's really, really easy to find roots of numbers over the real numbers. Like, we can take the cube root of this giant number here, no problem. But it's really, really hard to find nth roots of numbers over the integers mod some number. So, like, basically what I'm trying to get at is, like, well, think of it like this. So, like, it doesn't matter, like, n could be a bazillion times bigger, or it could be way, 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 way smaller. It has no effect. Like, as long as it's bigger than that, it has no effect on the outcome here. So we're not actually working over the integers mod some number. We're just kind of working over the real numbers, because it doesn't matter what n is. It could be, anything, as long as it's bigger than that. So unless you end up kind of looping past that number, you're just kind of working over the real numbers, and you can take roots in real numbers very, very easily. So that's why we can just take the cubed root of this number, no problem, because the plain text was too small. Now, kind of one of the things people ask is, like, well, how are you ever supposed to, like, figure this out or learn it? And basically, it's just because, like, this is kind of a problem you'll see a lot in CTFs, like beginner CTFs, or like, I mean, they did something similar to this to us when I was learning cryptography in uni. Like, it's just kind of like one of the examples that always comes up. But you could look and see, so like our modulus here is 2048 bits, two less than that, because when you convert to binary, you get a 0 B in front, so it's really 2048. And if you look at the size in bits of our ciphertext, it's a lot smaller, which basically, I won't get into the math behind that, but that just makes it pretty unlikely that this happened naturally. And we probably started out with plain text that was too small. So yeah, we can just take the cube root of this to get the answer. Really easy to do. Like, we could write a function that just binary searches for it, but I'm just going to use SymPy, which if you don't have it, you'd actually have to install it. Pip install SymPy. But oops. It's not, I mean, there's other ways. We could probably put that in Wolfram Alpha, I bet, and get it. I don't know if that's too big, but I'm just using SymPy because it's what I know off the top of my head. So we want the we want the cubed root of that number, and this true here is just telling us it's an actual root, not like it was real close and rounded or anything like that. Okay, so now part 3, Cliff Notes. This is too big now to factor, but they did a crappy job picking P and Q, so we can use Fermat factorization and factor it, and then we got P and Q, and then just like the first challenge, it's easy to solve. So Now, a little more in-depth version is if we look at this code here, this is how they're getting their primes, right? So Q, we assume, because this is just part of the code, they got the prime Q, and now they're trying to find a prime P. Well, they check, add 2 to it. They're checking if it's prime. Nope, add 2 more. Is that prime? Nope, add 2 more. Is that prime? Nope, blah, blah, blah. Do that until, yep, that's prime. And now they're taking P times Q. Well, so even though this number here is huge, and you'd look at it, so this is probably, I don't know, well, we're going to have to copy this anyway. So let's see how big it is. Looks like it's going to be 1,024 bits. That's my guess. I should actually know because, like I said, I've done this before. But I don't remember, or if I even did this. I did it. Length. Yeah, so, 1,023. So P and Q are 512-bit numbers. But this number here is, again, that's too big for us to factor. But it's only hard to factor if they pick P and Q correctly. And they did a bad job of that here. And I'll go over why they did a bad job. So let's look at like a little sideways graph of P and Q. Like say this is P and this is Q. So like a little bar graph, right? P and Q. Now let's look at the difference between P and Q. Now first off, we know that this difference is going to be even, right? Because P and Q are odd primes, so the difference between two odd numbers is always even. So we know then that there sits some number that's exactly in between these two numbers, and we'll call that number M. So like whatever this difference is, we'll just say it's X, right? Well, so this difference, there's a number that sits exactly in the middle of that, and let's say the top half is I and the bottom half is I. So basically, if we knew that number M, we could subtract I from it and get P, and we could add I to it and get Q. So we could say that Q is equal to M plus I, and we could say P is equal to M minus I. Now we already know, right, we know N equals PQ, so basically we could just substitute this in and say N equals M minus I times M plus I, right? And then if we do our FOIL, like if you learned that in school, first, outer, inner, last, like we're just going to expand this out, we are going to get N equals M squared plus MI minus MI minus I squared. And then these two cancel out, right? MI minus MI is just 0. Let's just move this down here. So we get N equals M squared minus I squared. Well, if we wanted to, we could add I squared to both sides, right? So we just get N plus I squared equals M squared. And so now let's think about this here. We know what N is, right? It's this big number that they gave us. And what if we just iterated over I's? Like I equals 1, I equals 2, I equals 3, blah, blah, blah. And we just take the square that number and add it to N and see if the result is a perfect square. Well, if we do that and it is a perfect square, then that means we could take the square root and we found M. And then since we were picking the I's, right, we would know then that Q is M plus I and P was M minus I. So we can just start out. Let's add 1 to N. Is that a perfect square? No. All right, let's add 4 to N. Is that a perfect square? No. Let's add 9. Perfect square? No. Let's add 16, and so on and so forth. And now you might think, either you're thinking like, well, that's going to take forever. We can't do it. Or you're thinking, why don't we do this for everything? And so the answer is, when, like, let's say, like I said, P and Q are roughly, they're 512-bit primes. Well, that distance between two randomly chosen 512-bit primes is so huge that it's impossible for us to iterate over it and find the answer. But when P is a 512-bit prime and Q is the very next 512-bit prime, it doesn't even have to be the very next one. But when P and Q we know are close together, then now this becomes computationally feasible. And like I could really nerd out and we could go into the math and I can tell you what the average distance is between two 512-bit primes. So that's about how many we would have to expect to go over. Well, divided by 2, right? Because anyway. So it's not very big at all. So they're close. So we can actually do that and solve that. So that's kind of like one of the problems you run into in RSA or rolling your own crypto anywhere is if you have to make sure you're doing it exactly right. Because if you aren't picking your primes right, then you fall victim to things like these. So, and the same way with the last one, like if you're not padding your messages, you fall victim to that, or can fall victim to that. So anyway, we can simply just write a function to do exactly what it is we described. We're going to take in and we're going to keep adding square numbers to it until we find a perfect square. And then once we do that, we'll have our P and Q. And then just like the first challenge, we can recover the plain text. So let's just write a function called Fermat. So this is Fermat factorization named after Pierre de Fermat. I can't remember if I already said that or if I did it in the video that I ruined, but you've probably heard of him, Fermat's last theorem. And if you do start getting into crypto a lot, you will use Fermat's little theorem all the time. Actually, let's just say, so while true. Now, since we know this is so close, like we don't have to worry we're going to get stuck in this loop because like we know that they're so close together. So let's say that test equals I is in. Oh, I didn't import. I wonder if I can import after the function. That'll be okay. Test equals in plus I squared. And then we will test for if is square. This is what I forgot to import. If that is a perfect square, then we found M, and it is going to be the square root of our test. And then we know that P is equal to M minus I, and Q is equal to M plus I. And we want to break out of that loop, and we want to iterate, make sure we iterate over things, and then we will return P and Q. And I need to make sure and import be in theory prime test is, so it's really easy computationally to check if a number is a perfect square or not, which is again why this is possible. And then simply import SimPy, import squirt. So now we should be able to say that P and Q are equal Fermat of N. All right, sweet. So P, Q, those look pretty close together. And then, actually, it's just so I can. So look, they were 40 numbers apart was how far apart P and Q were. So now we can do exactly like how we did in the first problem. We know that phi is P minus 1 times Q minus 1. And we know that D is equal to D is equal to power of E, the inverse of E to the power, to modulo phi. Oh yeah. So basically the way simply returns an integer instead of an int. So we are just going to say that phi equals int phi, and then we can do that. And now we know our plain text is equal to our ciphertext raised to the power of D mod n, and this is our answer. And that is how you do the RSA one. So let me go ahead and... Okay, so now on to the third challenge. Or fourth one, actually. So we'll do mac and cheese. So Cliff Notes on mac and cheese is basically read the Wikipedia page and it tells you exactly what to do. But actually, we're able, so Cliff Notes is if you have if you're allowed to input a variable length, if it's checking variable length messages, you can basically forge a signature, which that's kind of crappy Cliff Notes, but kind of not sure how to sum that up better. So like I said, it actually tells you on this. So if you go to the Wikipedia page, where is it? It basically tells you right here what you need to do. But actually, so let me just briefly go over CBC mode. So the way CBC works is we don't need to really know anything about AES here. We don't need to know what the key is. We don't need anything. You can just think of AES as this magic black box. It's a function. We put something in. What comes out looks completely random to us. And what CBC does is it takes, so AES takes 16-byte blocks. Everything has to come in blocks. And what it does is it takes the output from the previous block and XORs it with the input that's going into the next AES. So basically what that means is all the previous things affect the later things. So the reason you can use this, so like CBC MAC, basically MAC stands for message authentication. So what you would do is, like, say I want to send a message, and I want the person I'm sending it to, I want to allow them to know whether or not this message has been screwed with. So what I could do is basically a key me and this other person know. Like I'll encrypt this message, and then I'll take the last output from the encryption and I'll stick it onto the end of the message. I can just send the message in plain text. I don't care if anyone reads it. I just want to make sure who I'm sending it to can tell whether or not the message has been screwed with or not. So I'll stick the output of this ciphertext on the end of this message. So now when they get it, they can take the message, and since they also know the key, they can run it through the encryption, and they can compare and see, did the output of the last block match what I showed them? And if it does, then they know no one screwed with it. Because if you look what happens, say if someone flipped any bit anywhere in the message, what goes into the function is going to be different. So what comes out is going to be different. And then since that's propagating down the chain, what gets put into this is different. And then, so you'll get completely different last block, right? Because if any one bit has changed, this will be entirely different. And if me and this other person are the only one that knows the key, right? Someone else can't just change the message to whatever, encrypt it, stick what it then would be on the back, because they don't know the key, and you need to know the key to get the exact same output. So I don't know. Hopefully that made sense. So the way this attack works is, you can read it here on the wiki page. I'll try and explain it, but I'll use sort of the same format they're doing, so that if you need to go over it or whatever, like basically what I'm trying to say is I don't know how well I can explain. Like I don't know if I can explain it well enough that it'll make sense if it's confusing. So, but I will do my best. So basically, let's kind of look here. We'll say this is that M prime message, and we'll say like this here as like our plain text that we're putting in. So we'll say, right, we have according to the challenge, we can get a valid tag for 7 block messages, and then we're going to need to verify an 8 block message. So the way this attack is going to work is, let me get back to this. All right, so let's say, right, right, let's pretend there was, I'm just going to draw the end of this one, right? So this is the 6th block of plain text, and it's going to get XORed with whatever the previous one was. Here's our AES function, and what comes out is our 6th block of plain text or ciphertext, and that is going to get, here's our 7th block of plain text. It's going to get XORed with the 6th. Little arrows run through the AES function that we don't care how it works. It could be magic for all we care. And what comes out is that 7th block of plain text, which also is going to be our tag, right? Actually, are they using, again, I want to try and keep it the same. Oops. 2 pairs of, okay, so I'm doing that wrong. All right, so this is not M prime. This is M. This is our message M, and this is our tag T, right? So like whatever, these are all blocks, you know. So it looks like that did in that picture. Okay, so this tag will get appended on to the end of this message, and that's how we would verify that. Yep, no, that tag matches. When someone else tries to encrypt it with that same key, they can say, yep, tag's the same, message is the same. Well, now let's look at M prime. We can just some other message, like, so we'll say this is actually going to be the 1st block of plain text. So plain text block 1 on M prime, and it's going to get, oh, and the other important thing here is with CBC or CBC Mac, normally like in here, you see there's an initialization vector. In CBC Mac, the initialization vector is all zeros, just 0 bytes. So, and like we learned, anything XORed with 0 is just itself. So this first one, you basically, it's the same as if there is no initialization vector. And that will be important for reasons you will see, hopefully, in a minute. So we get AES, and this output here is our 1st block of plain text. And that's going to get sent up. And here's our 2nd block of plain text. Actually, let's, since I'm running out of room, let's ... all that stuff in the middle. And then this is our last block of plain text, right? That's getting XORed with the previous block 6 that we can't see because it's here in the fog of the wonderful math ... And here is our 7th ciphertext block, which is the tag for M prime. So T prime, M prime. So these are 2 separate messages, right? We could have either one of them is valid. Now, we can't send it to them and have it validated because, remember, we need to have them validate a message that's divisible by 8 blocks. But for either of these, we can get, we know we have a valid tag. Well, what would happen if ignoring the fact that we can only validate 8 block message, or blocks, a message divisible by 8 blocks. But just trying to just kind of describe why the tag they describe works. What if we concatenated these two messages together and we had a message that was m concatenated with m prime, right? And we ran that through CBC Mac. So this here would be, plain text block 1 of message 1. Ciphertext block 1, blah, 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 blah. On down the line, when we got to plain text block 7, AES is being XORed with whatever came out of the previous one. And then we got ciphertext 7. And then that's going to go to, this is the first block of plain text of M prime. It's going to go into our AES. And then we'll come out, and this is our first block of message prime. And then on down the line, blah, blah, blah. And the final one would be the 7th block of plain text in message prime. AES. And then our 7th block of message prime, which is also just the 14th block of that message, right? Because we're just saying it's one message, it's just 14 blocks. And this would be the tag for that. Now, this tag here is going to be different than, right, because we concatenated them. This, what this block and this block are the same. So use the pointer. This block and this block are the same. But when we stick the messages together, now everything from this point on forward is going to be different, because what's actually going into the A function now is the plain text block 1 of M prime XORed with the plain of ciphertext of M. And then so now what comes out is going to be different. So from this point on, it's different. But what if we slightly changed this message? So really kind of looking at these two things, the only thing that's different is that we are not XORing the output of this into this. Well, what if we changed this concatenated message slightly, and instead of doing that, we took M, then we actually went ahead and did this step. So then we put a block that is ciphertext 7 of M XORed with plain text 1 of M prime. That's this block. And then we just went ahead and just did like normal with all the rest of the blocks. So it's the rest of M prime. Well, now look what happens. If we made that our message, when this gets run through here, so now this block, where's my pointer? This block here is actually going to be this block. Well, look what happens. Like we learned from XOR, when we XOR, we've already XORed this in ahead of time. So now when we XOR ciphertext 7 XORed with plain text 1 of M prime, which we've said that this now is going to be that XORed with ciphertext, XORed with ciphertext 7. Well, like we've already learned, this cancels out with this, and so we're just left with this, which means what's actually going in here now is the exact same thing as what went in here on M prime, which means nothing changed coming out, which means the rest of this way down this chain is all going to be the same as these, which means that now this tag here is going to be exactly the same as t prime. So if we make our message this here, we craft it here, we use the original message, we make that special block, and then we just use the rest of m prime, we will get the exact same verification, the tag output, as what we got when we just got it for m prime. So hopefully that made sense. If not, I don't know, hopefully it made enough sense that you can kind of go over this and the wiki page and maybe kind of it'll start to make sense in your head. But what that means now is basically we can chain together, because we can get a valid tag for any 7 blocks we want. So we can just keep chaining 7 blocks together. Right? I just showed we could get a valid MAC for a 14 block. We could do the same thing, just keep doing this for a 21 block, a 28 block. Well, we have to enter in one that's divisible by 8, but we could just keep multiplying. 8 times 7 is 56, so we can just chain these all together until we've got one that's 56 blocks long, and we'll have a valid tag for that one. So that's honestly exactly what we're going to do. So let's call this Mac cheese.py. So let me think of a good way to do this. Because so basically we're going to have to be interacting with, actually we could do this one manually, but I did kind of, I want to show, I guess, Pwn tools a little bit, not a little bit, but so like, right, this is how we would do it normally, but we can do that programmatically in Python by using a package called Pwn tools. Oops. Import everything. Which, here, it is. So you can find it here. Like if you start doing CTFs or do a lot of CTFs, like it's definitely a tool worth using, like you want to use. Now, I don't know it very well. I just kind of know the bare minimums. But like, so let me just go ahead and I'll show just the tiniest little bit, just so what I'm going to do to shortcut, because I don't want the video to be that too long. We are going to let's say port. So basically we can do the same thing. We can do it programmatically. So I'm initiating a connection to the server, and then I am going to say let's just say blah equals IO. And then we'll print blah. And then I'll run that just so you can see kind of what it's doing. So see, it connects to the server, and then it gives us this first line. If we wanted it to do everything. So again, I know the bare minimum of Pwn tools, so there's probably better ways to do this, but you could say received until, which would you like to do? I'll just do the end of that. Like to do question mark. And we'll make that a byte string because it gives you a warning unless you don't. So see, now it gets received all that, received it all the way up to there. And then we could enter, like, so let's say we wanted to give it 1. So now, like, if we were doing it manually, we'd say 1, but we can do that in Pwn tools by saying IO IO send line, we will send it the line 1, and then let's receive, and then we'll print just to show that it. Oh, did I? Is it space? Send. There we go. There was a space after. Well, and see, then it printed all that. So basically, that's kind of how you can do it. And then you can sort of figure out the format. And then what I'm going to do is copy and paste what I did in the other one just to kind of speed this up some. So we're going to get rid of this. So basically, I just wrote 2 functions that basically repeat all that. If I want to get the HMAC, this will do it for me, and it'll get me that. I don't need that. It'll return the tag in bytes, and if I want to verify one, it does the steps like you would manually, and it returns the result. And then so we can initialize our connection, and then now we can kind of go about our problem. Like what I'm going to do, so like how I showed here, this M and M prime, what I'm going to do is I'm going to make all our messages, every block is just going to be all zeros. And the reason I'm going to do that is because then it makes this step here easier, because remember, anything encrypted with 0, or not encrypted, anything XORed with 0 is just itself. So whatever this tag is, when we XOR it with the input to the next block, since these blocks are always going to be 0, we can just make it the tag. So that just kind of makes it a little bit simpler. So then we can get the tag. So we'll call that function that I wrote that just, first let's create our block. So our block is going to be the byte value 0 16 times, or actually 112 times, because we want our blocks have to be our message. That's actually what I should call this instead of block. Our M is a block of null bytes, 7 of those blocks. And our tag is going to be, to get the tag from M, we're going to give it the connection. And then we can create, we'll call it M that for M prime. And that is going to be this block, special block we make, and the rest of M. But remember, since I'm doing that kind of shortcut, it's just going to be the tag and then 6 blocks of null bytes. So our M prime, or M underscore, is just going to be the tag plus 6 blocks of null bytes. And then, so we could say that our final message, our final M, right, and this is the one where we're going to want to chain all those together. That will be our M plus our 7 blocks of M prime, right, the special ones we made, and then plus we've said that we're going to make it, we know that the final tag is going to be the result of just that message by itself, and since we know now the tag of that message by itself is just the tag, we can add that to the end. So this is 7 Each one of these is 7 blocks times 7, so that's 49 blocks, plus our original one that was 7 blocks is 56 blocks. So this is a 56 block long message, and this is the tag that validates it. So now we can send that to our verify and then give it that, and then we will print out the flag. And where did I call something final block? Oh. Oh yeah, why did I call it that? That should be called message. What you get for copy and pasting stuff. And that should be, yeah, I called it block here. Oh, that should be message, whatever. Just be consistent, and it's for a CTF, and it's just copy pasting, so whatever. So yeah, there we go. We do that, and that is how you get the flag for that one. So hopefully that kind of makes sense. And now we will go on to the last one. So last one, Cliff Notes. This is a CBC padding oracle attack. So basically you just do a CBC padding oracle and you will get through that. Now this one also I'm not going to go super in depth in because there is a bazillion, like this is a really kind of famous one, and there's a bazillion better resources. I've even well, actually I'll go over that. I'll kind of go over it a little bit, but so basically, so the way PKCS padding works is, I don't need that. Excuse me. So AES, you have to send it a full block. So what happens then if your message isn't divisible by 16 bytes? Well, you have to pad your message, right? Because they have to be blocks. Here, let me go ahead and PKCS 7. Solution. Sorry, my brain is not working. So if you are short, 1 byte short of filling up a block, padding will add in the byte value. Python's going to make it look ugly. It'll add a byte of 1, right? It'll add the byte 1. If you're 2 bytes short of a full block, it will add 2 bytes of the byte value 3. Now, guess what it's going to add if you're 3 blocks short? You guessed it, 3 bytes of the byte value 3. The other thing is padding is mandatory. There always is at least 1 byte of padding, which means if you send it something that's exactly 16 byte, like it fills up all the blocks, it's still going to add padding. This time it's going to add a full block of padding. So it'll be a block of the byte value 16 bytes. So this is in hex. So this is 16 in hex. So it'll be this 16 times. So it'll be a whole block of padding. Now the way padding oracle attack works is, so like let's say padding oracle is basically just an oracle, right? It tells us whether or not there's correct padding. Doesn't tell us anything about the key, doesn't tell us what it decrypts to, doesn't tell us anything. It just tells us, yep, that's valid padding. Now you might think like, well, how are you ever gonna, this is kind of artificial, but like in the wild, you'll find that, well, you won't find this a lot anymore, but like if the service isn't handling things correctly, it's pretty easy to see how you could end up in a situation where you could tell whether or not you get valid padding. Like let's say if there's not valid padding, it'll throw an error. Like the program it'll shit the bed in the background. So if you send it something that doesn't have valid padding, and they didn't correctly, say they're not expecting the user to change, say they're just encrypting cookies. So they're not thinking about security, and they're not expecting like, oh, why would the user ever like go in and manually change this? So they're not accounting for error coding or error correction or handling errors, sorry. And then, yeah, it throws an error, and then you get a stack trace back, or maybe you get a 500 response, or let's say, not even that, but let's say in handling the error or something happens, you can actually tell, oh, if this response takes longer, that means there was an error, invalid padding. Or maybe if there is invalid padding, a whole bunch of other stuff doesn't happen. So if the padding is valid, the response takes longer. It's like any way you can find that'll tell you whether or not it's valid padding. That's all you need to know. Is this padding valid or not? And you can recover the message. So that's kind of, in a nutshell, the idea behind it. The way it actually works is, I'll briefly go over that. But so like these are all chained together, right? So let's say we can change it. Like we have control over the ciphertext, right? This is what we're giving them. Now, if we give them something that wasn't originally a message, we're just going to get, gobbledygook back, or it's going to decrypt to gobbledygook. But we control what we give them. We can give them anything. So we can take a valid ciphertext that will decrypt to a real message, and let's say we can change this block here. Well, look what happens. If we change this block here, it's getting XOR'd with the output of here. So yeah, everything that comes out of here is going to be gobbledygook. And then because we're changing stuff here, now everything that comes out of here the plain text is going to be gobbledygook. But the important thing to know is what actually first comes out of this AES function is called the key stream. So this is the actual ciphertext. It'll decrypt under the key we don't know, and we'll get the key stream for that decryption of that ciphertext under this key. And then it'll get XOR'd with, we just changed it to all random stuff. So it's going to XOR with random, and it's just going to be a random mess here. But we know that padding is mandatory, and it's checking for padding. So when it checks for padding, there's only a specific number of ways this message can end, right? If it doesn't end in XO1 and then this is something else, you know what I mean? Like this will be invalid. If it ends in XO2, this has to be XO2, and then this has to be different. Otherwise, it won't be valid, right? So we can make all of this random, which is going to make all of this random. And then we can test. We can iterate over every single byte. We'll make it a 0. We'll make it a 1. We'll make it a 2. And we'll keep doing that until the oracle says, oh, it's going to say invalid padding, invalid padding. And then one time it's going to say valid padding. Well, when it's valid padding, then we know that this last byte here is a 1, which means we were controlling what this is. We now know that this decrypted to the value 1, so we can XOR those two things together and get what the last byte of keystream is. Now that we know this last byte of keystream, we know what we can make that so that when it XORs together, it'll get a 2 here, and then we'll just do the same thing here. We'll iterate over all of these until eventually we get one where it's a XO2 here. So then we had XO2, XO2, and it goes, oh, that's valid padding. And then now we can do that process again, and so now we know the last 2 bytes of keystream. And we just keep on doing that until we recover the entire keystream, and then we can take that keystream and we'll XOR it with what the ciphertext actually should have been, and then we will get what the actual valid, we'll recover that block of plaintext. And we can just keep on working our way back. And the way we're actually going to do it in this attack is, one thing is, we only have control over the ciphertext, right? We can't change the initialization vector. So we won't be able to recover the very first block. Like we can't get this because we would need to manipulate this. But we'll be able to get everything else on down the line. And we're going to just do, on our attack, we're going to do it 2 blocks at a time. We're going to send them 2 blocks, this will be the block we want to figure out, and then this will be the block we're changing, and we'll know what it was originally, and then we're just going to do that. So again, I'm not going to go super in depth. Hopefully that kind of made sense, but this is pretty famous, so there's a lot of stuff on it. There's actually, if you do the CryptoPals challenges, which if you're wanting to get into cryptography or whatever, or learning more about crypto, I would encourage you to do, because they're pretty good. Also, even better is go to cryptohack.org. Great site. Their Discord is awesome. Everyone's super friendly. Like, it really, really, really will help you learn cryptography, especially for like these kind of challenges. But what I'm actually going to do is basically just copy paste the code. So this challenge, CryptoPals challenge 17, is this exact attack. If you're interested, I have videos where I really go into depth in the CryptoPals. Like, you build everything up from like the ground up. So that's what's going on with this. So, but I'm just, for the sake of brevity and this not being forever long, I'm just going to, we're just going to steal the code I've already written, because it's basically going to do exactly what we want it to do, because it's literally the exact same attack. And then we need this output. So this is the output they gave us. It's just directly, oops, what this file is, the CTF hex here. So we will say, and then we're going to use Pwn tools again, because that's how we're going to interact. Did I start this? Let's go ahead and start this. So we're going to say this is our ciphertext. We want to get that into bytes. We're going to use Pwn tools. And we want, and then I'll kind of briefly step over what this is doing. So we're not in a function, we don't need that. So basically, we are carving this message up into the blocks, and then this is going to be our recovered plaintext, and this previous block we're going to be sending two blocks at a time. So we need to know, like I showed here, we need to know what this is originally before we start changing it, because once we recover the key stream, that's what we're going to XOR the key stream with what this originally was. That's how we're going to get the plaintext. So we, like I said, we can't ever recover the first block, so we're going to ignore the first block. That's why we're starting at 16, because we're ignoring this first block. So this will be, let's see, how long is this? This is, if I remember from the other video, so 128 characters long, so it's 64 bytes, which means this is 4 blocks long. So we'll be able to recover the last 3 blocks. So this CT blocks is a list of 3 blocks. So the first time through, we're going to get the first block, because we can change the first block, but we can't ever recover the first block, if that makes sense. And then we're just going to iterate over this list. The IV here is just going to be the one we're changing. And then this is a key stream. Initially, we don't know any of the key stream, right? So that's why it's blank. And then, like I said, we know what we're going to want this to be. Is the first time through, we want it to be a 1. Then we're going to want these to be 2s. Then we're going to want these to be 3s. So that's why we're iterating from 1 through 16. Because that's what we're looking for the last time through. We'll want 16, all of these to be 16. And then for B in range 0 to 256, so that's just the range of all possible byte values. And then this line here is actually, oh, I need to change that, because in CryptoPals we built our own XOR function, and it's different than the XOR from Pwn tools. Basically, this line here is the step of, whoops, I don't like that one as much. Like, well, say we figured out this was, we know the first byte here. Well, so then next time through, we need to make sure this is a 2, so that we can, when we're iterating, when we hit what's a 2 here, we're right. And so the same thing, like if if we were looking for 3, we need to make sure that this is a 2 and this is a 2, or sorry, this is a 3 and this is a 3. So this line here is basically, we know those bytes of key streams, so we're finding out what we need to actually make these so that when it's XORed, we get the appropriate one. So if like we're looking for the 3rd byte of key stream, we want to manipulate it so this is XO3, XO3, and while we iterate over that one, so we need to make these whatever it needs to be, so when they're XORed, those RO3 while we're iterating over this one. So that's what that line does. And then this line here was our oracle. We'll just make a function called isValid padding, where we will pass in, like I said, we're going to be doing it 2 blocks at a time. So we'll pass in the one we're randomizing and then iterating over, and then the one that we're actually trying to recover. This here is getting that byte of key stream. So once we hit it, yep, that's valid padding. Like I said, we know what this is now. We know what this is because we controlled it, so we can XOR them together to get that byte of key stream. This is, once we're finally done, we've recovered the entire key stream. So we XOR it with the previous block, and that's how we recover that actual thing of plain text. And then that should be it. We just need to write our we're using Pwn tool, so we need to connect. So like, I'll show the challenge. I should show it. Now in here it says you need to use multi-threaded, and that would make it faster, but it's not so slow that, oops, where am I going? That you can recover it anyway. So like, say we're gonna validate, so this won't be right. It'll tell us there's an error because it's not the appropriate length. But basically, same thing as the other one. We're just gonna manually do that with Pwn tool. So we are going to connect to and then again, I always make this port just because then it makes it easier when I want to do the script, or if it times out or whatever, then all I have to do is just change the port instead of trying to scan through the code to see where I actually put that line. And then we'll receive until, so we're going to receive until choice. Oh, choice. And then we'll write our, oops, we need to write our oracle function. Message. So then, let's see, we send line. I need to give it the IO. Actually, I don't. This would work if I didn't because global variable, but oops, type. So we're sending it that, and then we receive. Now I remember what it is because, like I said, I've done all this already, but I'm not bitter. And then we're going to send our message. It wants it in hex, and then we want to make those hex bytes. So this is kind of where it gets confusing with Python and byte strings sometimes. So it wants the message in hex, and what we're passing in here, these are byte values because we've been XORing them. So we're going to change the bytes to a hex value, but then we're actually sending bytes. So what we're doing is we're actually like, so if we have F, we want let me make this. Right, so this is a string of Fs. We want it to see that string of Fs. It's going to know it's hex, and it's going to convert it to hex. But since we're sending bytes, we still have to encode it. So now it's a byte string of Fs, but it's going to know to treat these as hex values, not the actual byte values for what F is, if that makes sense. And it might not, because that used to confuse the hell out of me. And I don't think I explained it in a way that probably made it any better if you're confused. But so then we're going to get to response. We'll strip off the new line character. And like I said, because and then we're going to tell it it needs to receive until choice. Again, that way we're set up in the right spot for the next time we call the oracle. And because I remember what it is. Now, if you're like, oh, well, how would I know what a valid response is? To know, like, when you give it a correct answer, how do you know what you got is right? But since we know that this is valid padding, like we can give it the original message we got because we know this will decrypt correctly. So that's how we can test to find out, like, oh, when we give it something correct, it says valid. That should work. So this is going to take some time. So I want to give it something so we just don't stare at a blank screen. So let me, we're going to use the logging function from Pwn Tools, and we'll say P is log progress, and we'll say working. And then down in here, we'll say P status. We'll show what I and what B we are on. And then when we're done, here we'll actually go out. I wonder if I could do it this way. I don't know if this will work or not, if it updates the way, or if it just takes that F string once. Oh yeah, it would, because that's just because the variable change shouldn't matter. Would I want to do that then? You know, I'm going to do it anyway, because I'm pretty sure that this won't work for what I think it's going to do, but then I'll know, and so now I'll learn something. I'll just print out the old-fashioned way each time through, print what are the flag we've gotten, and then when we're done, we'll say P success. We recovered the flag, and we'll print what the plain text was, which should be enough of the flag. Well, I know it is because I did this challenge. That should work. So now we should be able to just run it. If I fix all my typos. Message is not defined. Oh. Again, copy pasting. I didn't change everything the right way. So this is actually ciphertext, right? Because we're using this. And in the CryptoPals ones, I was calling it something else. Now it should work. No. Oh, yeah, oops. Is all the padding. We have to give it our, which we actually don't, but, well, we do because I told it we needed to, but we could have just done it and not. Oh, Texas. That's here. I'll just, that doesn't matter, but just so it looks better. Where is that part? Oh, I didn't give it bytes here. So we can see it's connected, and now we can see it's working. So far we have none of the flag. I don't think this is going to update, but then maybe it will. I don't know. Like I said, I'll learn something. So we're on 1 and 52. So this is the last challenge. So I'm just going to let this run, and then hopefully I can figure out how to edit and make it speed up and look cool. Well, it won't look cool, but if not, I'll just bam. Now all of a sudden we're done. So we'll see which way it is. And there we go. That is the flag. So that is the completion of the last challenge. So if anyone watched this video, I hope you got something out of it. I hope you were able to learn something. If you have any questions, or I didn't explain something well, or just any questions at all, feel free to leave a comment or hit me up on Discord or Twitter or wherever. I'm always happy to talk about crypto or any of this hacking stuff. So if somehow someone made it all the way through this and is listening, like, yeah, I appreciate it. I hope you learned something. I hope you enjoyed the CTF. And yeah, take care. Bye.